A telescoping series always proves convergence. You just have to show that a telescope. So usually what's going to eventually involve is you plugging in numbers into that series, writing down a string of numbers, and then you showing that at least four in a row are canceling out. Okay. There are some series out there where a couple might cancel at the beginning there, but it ends up not being a telescoping series. So you need to make sure you show four in a row, not a couple, skip a couple, and then a couple more. Four in a row, four consecutive things are going to cancel out there. And if you can show that, everything else will cancel out after that, and it's going to be a telescoping series, and those always converge. Okay, so this Nth term test, geometric series proves convergence or divergence. Nth term test only proves diverge. Telescoping series only prove converges right there. So this example, though, if you plugged in 1, plugged in 2, plugged in 3, plugged in 4 for the ends, you're getting this string of numbers. And that right there, that does not look like a telescoping series. Nothing is canceling out there. Also, I'm not multiplying by the same number each time, so it's not a geometric series. So you're thinking, okay, if it's not telescoping and if it's not geometric, what about the nth term test? I got a nice rational function right there. Let's do that limit as n approaches infinity. But here you got 1 over n squared. That degree on the bottom is larger, which means that's equal to 0. So remember your nth term test. If you do that limit as n approaches infinity of that original term, then if you get 0, that means that test is inconclusive. So nth term test is inconclusive, but at least I would have that in my head. Just look at that real quick, know that I'm going to get 0, and eliminate that from an option of working. I know that's not going to be an nth term test. So that leads us back to, hey, I only know a few tests at this point. There'll be another test we learn in the future that will also work on this, but right now, the telescoping series is going to be our best bet. But if it's not a telescoping at the beginning, here's what we can do. Is you might wonder, this is something we did last chapter reviewed. If you have a fraction like that and you want to kind of break that up and you want to get separate things involved, use partial fractions, all right? Those are two linear factors. So I can make this like a over n plus b over n plus 2. All right, so that's like a hint there to use the partial fractions on that. And then remember how we find those. We put the numerators together, right? So we have a times the n plus 2 plus b times the n, and you set it equal to the original numerator, which is equal to 1, and then we choose those easy values of n. That's going to help us get that a and b. So if I choose n equals -2, that's -2 plus 2. That means the a term is going to go away. So if I plug in -2 for that n, we'll get -2b is equal to 1, so which means the b is equal to a -1/2. And if I choose n is equal to 0, that b term will go away, and then 0 plus 2 will get 2a equals 1. A is equal to 1/2. So if you want a further review of your partial fractions, rewatch your 8.5, your partial fraction video there. And then now we can take those numbers and plug those in. So now we have the summation. We got the 1/2 over the n, and then plug in the -1/2 for the b. So we have -1/2 over that n plus 2. All right, and here's what I always like to do. Instead of plugging in now, going from n equals 1 to infinity, getting all these fractions and stuff involved, you're allowed to pull out that number. It's a number, just like you could pull numbers out in front of the integral. You could pull the 1/2 out in front of that summation notation, and what we're left with is the 1 over n minus the 1 over n plus 2. Now, in the future, if you ever see, this is a common thing, if you ever saw this as your original problem and you saw fractions broken up, I want you to plug in right away, see if you can show that that thing telescopes. Now, it may or may not telescope, but if you see fractions broken up, that's your best bet at the beginning, because if it doesn't telescope, then we'll probably have to put that stuff together and use some other test that we're going to learn in the future, right? But now, so now that you got those broken up, so it didn't telescope at the beginning, we used that partial fraction technique, and now let's just plug in. So that 1/2 is going to stay out there, and now let's plug in the 1 for the n. So if I plug in 1 for both of the ends, I'm going to get a 1 minus 1/3. Do not put those together and make that 2/3, because then you're not going to see that at telescope. So just leave them separated like that and just write them down every single number. And if I plug in 2 for the ends, I'm going to get 1 over 2. If I plug in 2 for that end, that's going to give me a -1/4. Again, just leave them separated like that. If I plug in 3 for the ends, I'm going to get +1/3, -1/5. If I plug in 4 for the ends, I'll get +1/4, -1/6. And once you get a string of numbers, then let's see if we can get some to cancel out here. Okay, so I got a -1/3, +1/3. I have a -1/4, +1/4. I see 4, I don't see 4 in a row yet. So if I don't see 4 in a row yet, 4 consecutive things that are canceling, then I'm just going to keep going here. So what did I left off on? 4. So now I'm going to plug in 5 for the inside. Give me plus 1/5 minus 1/7. You can plug in 6, you can plug in 7, plug in a bunch here, just get a string of numbers. But then once you notice, so like right here, now I have a minus 1/5 and a plus 1/5. And right there are my 4 in a row that are canceling out. So that's what you need to show. This is your work. This is your justification for this problem right there. That's what you need to show to prove that something telescopes. Now, once you show that those 4 in a row cancel out, it's going to assume that everything else after that will eventually cancel out, because you're thinking, what about that negative 1/6? Well, your next term is you're going to plug in 6 and you're going to get a plus 1/6 minus 1/8, and see, then those 1/6 would also cancel out. So everything is going to cancel out once you establish that those 4 in a row cancel out. So that's your work. And so if we say converge or diverge, telescoping series always converge. So we're just going to put converge down. And then you always got to tell me converge or diverge, and always tell me the test that you're using to determine that. You're using the telescoping series test. All right, so just break down telescoping. Don't put TS or GS, or don't use your weird abbreviations there. Make sure we tell clearly and you're using the type of the test that we're supposed to be using. So tell me converge or diverge always, and then tell me the test that you're using. And if this is a telescoping series, we need the partial fraction work. We won't always need partial fraction work, because sometimes the original problem might be like this. So then all our work is just plugging in and showing that those 4 in a row cancel out. Now, we won't always ask you to find the sum. All right, sometimes we can't even find the sum, or in order to find the sum, then you need to know something a little bit more advanced that we'll learn later on in the year. But right now, we're just kind of determining, does it have a sum or not? That's what that converge word is going to tell us. Now, if it's a geometric series, we can use that a/1 minus r formula to find the sum. If it's a telescoping series, we can always easily find the sum. If I ask you to find the sum, it's either geometric or telescoping. And if it's telescoping, the way you find the sum, there's no formula for it. It's just whatever is left at the beginning, the stragglers left at the beginning, before you hit that 4 in a row that canceled out, those are the ones that are left. That's going to be your sum. So I would carry down the 1/2. And then you have 1 plus the 1/2. That's going to give us a 3/2. And that's going to give us 3/4 right there. You're only concerned with those stragglers left at the beginning, because once you hit those 4 in a row, everything else after that is going to cancel out if you keep plugging numbers in all the way up to infinity right there. So those are the ones that left at the beginning. So if I ask you to find the sum, it's just those numbers. Be careful, make sure you carry down the 1/2 and 3/4. That just means if you kept adding up a bunch of those numbers, if you wrote down like 50 of those terms and add those all up, that answer is going to be really, really close to that 3/4. And then the more that you add up, the closer it's going to get to that 3/4 right there. And then just one final thing, when you're working out the homework there, the beginning of the assignment is talking about this S sub 1, S sub 2, S sub 3. Those are called partial sums. S sub 1 is just your first term. S sub 2 is the sum of the first 2 terms of your series there. S sub 3 is the sum of the first 3 numbers there. And so S sub 2, you just add up like the first 2 numbers. S sub 3, you add up the first 3 numbers, and you kind of write those down there. And then just please model the notes as you're going through the examples for your thing. And then this section only has a few of the tests in there. So just kind of model those and try to get that recognition down now as you're going through each section, like when you're using each test.